Hey math students! Today's lesson is focusing on properties of logarithms and the unique relationship between exponents and logs. So we're going to start off with a warm-up. I want you to just take note of the directions of the warm-up is to write the expressions with all positive exponents. So your final solution should have only positive exponents. Take about 5 minutes to try these problems and then come back and I'll go over my solution. So here's what I got. Here's my solution. In the first problem, part A, really just focusing on combining like terms, which means like multiplying 2 and 4 together, and then combining x to the negative 1 with x squared. And then once we do that, we have this simple expression down below. And we just have to divide by x and y. So that is our solution there. Part B looks a little scary, but as long as you remember that anything raised to the 0 exponent is just 1, you're good. So that whole numerator just simplifies down to 1 because it's being raised to the 0 power. And at that point, we just have to turn these negative powers positive, since our solutions are only supposed to have positive exponents. And we can do that by moving them up to the numerator. So that is the solution for the warm-up. Now let's learn some properties of logs. We have another table, yes, so take a minute to pause the video and copy down this table. And after copying down the table, I hope that as you're writing them down, you're like, these are pretty similar to my properties of exponents. Logs and exponents seem a little similar, and you'd be correct. So let's practice applying these rules. Similar to exponents, logs do, in order to combine them or to apply these properties, they do have to have the same base. So logs always have a base, and in this case we're just using a generic base b. So the product rule for logs says that if you are adding two logs that have the same base, you can combine them by multiplying together what is inside the argument. So I had m and n in two separate logs, but when I combine them together, you multiply m times n. Okay, so in the example, I can see that they have the same base. Both the logs have a base of 3. And so in order to combine it together into a single log base 3, I'm going to multiply 4 times 2, which is 8. We multiply the numbers together. Similarly, if I wanted to, look, I wrote lob. This should say log. So if I wanted to combine two logs that are being subtracted, essentially, if there's a minus sign in front of the log, instead of multiplying, you'll divide by whatever that number is. So since we are subtracting log of n, then that n is what we divide by. So the minus sign indicates that we're going to end up dividing by that value when we combine it into a single log. So in this case, I have log of 12 minus log of 3. And I want to remind you, if you have a log that has no base, so I see right here, there's nothing there. This is kind of similar to square roots, where if you just have a square root that's blank, you know that there's a 2. The default for logs is log of base 10. Okay. So combining these two log base 10s, I am going to divide and make sure that I'm dividing by whatever's being subtracted. So that means the 3 goes in the denominator, and this ends up being log base 10 of 4. I squeezed it in. So a log, like if I have log b of m, just so you know how to pronounce it, this is pronounced log base b of m. So for those who need a little pronunciation guide, it's pronounced log base b of m. Why don't you try real quick? Log base b of m. I know you said it out loud. I have faith. I trust you. You definitely said it out loud. Okay. Next up is the power rule. And so the power rule is applied when you have a constant, a number that's being multiplied by a log. So if you're multiplying a number by a log, that number can become the power of whatever is in the argument. So m is being raised to the power of n. So you can move the constant to become a power. Interesting. So in this case, I'm multiplying by a constant of 2. And so I can rewrite this as log base 5 of 4 squared. So the 2 comes up there as the power now. So this is log base 5 of 16. And then finally, the natural log, ln. You've probably seen ln. So this is just reminding you that ln base e, or log base e, is just referred to as the natural log. Okay? So instead of writing log base e, we just write ln. Okay. And ln of e is very special. So since ln is log base e, then log base e of e is just 1. So ln of e is 1. Because if you have the same thing in the base as what's in the parentheses, similar to right here, these are very similar problems. So if I have log base a of a, it just simplifies to 1. Okay, so ln of e also equals 1. So in the little yellow box below, there are some logs and ln's, natural logs, that you should just have memorized. So ln or log of 1, both of these are just equal to 0. So log of 1 or ln of 1, both are 0. Ln of 0 or log of 0. You should know this actually. Can I plug 0 into a log? Is 0 in the domain of log? And I should hear you say no. I thought only positive numbers could go into log. You'd be correct. So this one is undefined. You cannot plug 0 or negative numbers into a log or a natural log. So here are some properties that you should have memorized. We're going to use it to solve these problems. So this is going to involve us using both properties of logs and properties of exponents, because we are amazing and we know both. So we want our logs to end up being in this form. So essentially this means only one log. So I see all these problems have multiple logs, like there's 2 log expressions. We need to combine them all into one log, where everything is in the argument. So there's no numbers being multiplied out front. It's a log where everything is in the argument, and it's written in this form. Okay, so this form should look familiar. It's the same form that we simplified our exponents into in our exponents examples. So, part A. So I see there's a couple rules that I'm going to have to do. I see that I have this constant that's being multiplied in the front that I need to get rid of. And then I have this subtraction sign. So the 2 rules I'm going to use is the quotient rule because of the subtraction, and also the power rule. Okay, so So I'm going to apply the power rule first. I'm going to take that 2 and I'm going to turn it into a power like that. Okay. And now I can apply the quotient rule. So when I combine these together into one log, base 8, I'm going to use division, the quotient rule. So what's on top is going to be this 3a squared, which I can rewrite as 9a squared. And then in the denominator is b. Okay, I'm almost done. I just see that, remember, I need to keep the argument in this form. So that form means no fractions inside the argument. So I need to get rid of the fraction inside the argument, and I can do that by using my rules of exponents. So I'm going to turn this b to the positive 1 in the denominator into b to the negative 1 in the numerator. So I just moved the b up using my negative exponent rules. And now it looks like the form that I'm supposed to have it in, so this is the final answer. Cool. Part B, very similar. I see I'm going to have to use my product rule and my power rule again. So I'll start off just using the power rule. So, oh, and also, I see that I have a log base e. So instead of writing log base e is ln. So I'll write ln of 4 plus ln of 27a to the 1/3 power. And now I'll use my product rule to combine those together. So ln of 4 times 27 to the 1/3, that's the cube root of 27. The cube root of 27 is 3. And then a to the 1/3 we'll just leave like that. So that equals ln of 12, a to the 1/3. That answer looks good. It looks similar to the form we're supposed to keep it in, so that is it. C, I think, is actually the easiest example. So we just did those 2 hard ones. I want you to try this one on your own. Alright, here's what I got. So I ended up turning b to a -3 power, the power of -3, because remember we want to keep it in that form. Over here, we want to keep it in this form with no fractions. Okay, cool. So the last thing that we want to learn about with logs is its relationship to exponents. And the big relationship that I'm going to reveal is that logs and exponents are inverses of each other. So similar to how addition and subtraction are inverses, multiplication and division are inverses, the square and the square root are inverses. That's all the inverses I got right now. So those are inverses. Logs and exponents are also inverses. So now you can add these two. So log base b and an exponent with a base of b are inverses of each other. And we can see that with their graphs. So I'm going to do quick sketches of what their graphs look like. So a log looks like this, where there's an asymptote right here at 0, because remember, logs can't equal 0 and they can't be negative, and it goes through the point 1, 0, because I know that log or ln of 1 equals 0, right? That's one that I wanted you to memorize. ln of 1 equals 0, or log of 1 equals 0. So that's how I know it goes through that point. There's a log, and then an exponent looks like this. There's an asymptote here now, and it goes like that, and it goes through the point, 0, 1. So remember, inverses always switch their points, and you can kind of see, if I were to draw the line of symmetry, so the line of symmetry is here in both the graphs, they are a reflection of each other over the line of symmetry. So logs and exponents are inverses. Oops! I totally wrote where I was supposed to write the domain and range. That's okay. So the domain of my log goes from 0 to infinity, and the range goes from negative infinity to positive infinity. You can see that in the graph. And so since they're inverses, exponentials or exponents are going to have the opposite. So they're going to be switched. The domain of an exponential function goes from negative infinity to positive infinity. And then the range goes from 0 to infinity. So they're swapped. Pretty cool, huh? And so since they're inverses, they can be used to like cancel each other out. So right here, I have a log base b, and remember, it's so important that the bases are the same. So if you have a log base b, and then inside the argument of the log base b, you have an exponent with base b, they cancel each other out. So just the same way that all these other inverses cancel each other out, logs and exponents cancel each other out too. So the log and the exponent would cancel each other out, and we'd just be left with x. And I could write this the other way around too. So if I had an exponent with base b, and in the exponent was a log with base b of x, the exponent and the log cancel each other out, and I would just be left with x. So that's why I have the equal signs on both sides, to show that they cancel out just the same way. And then this is like a little trick for converting between logs and exponents. If I had a log and I wanted to convert this log into an exponent, what I could do is I would keep the base the same. So my exponent would have the same base, b, but I would move the x to become the exponent and the a to the other side. So x becomes the exponent and a goes right there. So this is just a little trick for converting between logs and exponents. So example 2, use the fact that logs and exponents are inverses to solve the equations for x. Alrighty, I'll do that. So right here, I want to get x by itself. So here I can actually use my logs and exponents conversion. So I can convert this log, because right now I can't solve this. I'm like, that x is stuck in the base. I can't solve this equation, but maybe I'll be able to solve it if I convert it to an exponent. So I'm going to switch the 2 and the 5 to convert this to an exponent. My base will stay x, the new exponent is 2, and it equals 5. And so now I have an equation that I can solve. This is a solvable equation. I just take the square root. So x equals plus or minus the square root of 5. And I'm done. Here we have another problem. We have to use multiple skills here. The first thing I'm going to do is I see that I have a ln of e. And so remember, ln is the same as log base e of e to the 7. And so this is a case of the log and the exponent, since they have the same base, they cancel each other out. So I have log base e and an exponent of base e will cancel each other out, and I'll be left with 5x equals 7. So I just used this rule right here. I used that rule right there to turn that into just 7. Okay, so this equation looks a lot easier, but I still have x in the exponent, and I can't solve this problem. So we're going to try to solve it by now converting this exponent into a log. So I'm going to convert this exponent into a log. I'm going to keep the same base. I'm going to use the conversion, but now basically the x will move and the 7 will come over. So I'm going to have a log base 5. Instead, I'm going to have the 7 in the argument, and it equals x. So now I have solved for x. Woohoo! Okay. Last one. Ooh! Ooh! This one looks tricky. I do see that I can probably use this rule right here. Right? Where I have a base with a log with the same base. So I'm able to use this rule. But I have to be a little careful. So, if you need help seeing how I can cancel out, I'm going to turn this into a log base e of ln of x equals 8. Like that. And so then my e with the log base e cancel each other out, but I'm still left with this ln of x equals 8. Okay, so I have ln of x equals 8. In this, I can use my log conversion to solve for x. So I know that ln has a base of e. So remember, there's like a base of e. I'm going to keep the base the same, and I'm going to switch these. So 8 will become the exponent, and x will move over. So e to the 8th power will equal x. And that's it. I could put it in a calculator and figure out what those two things equal, but I was really just asked to solve for x, and I did. So I relied heavily on these two rules right here. The fact that logs and exponents with the same base cancel each other out, and the fact that you can convert between logs and exponents.